Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and this is the third installment for circuit analysis. Today, we're going to be talking about switches, power, independent, and dependent voltage and current sources, where these, similar to the past two videos that I published, are fundamental materials that every electrical engineer should know. As a result, in this lecture, we will introduce these four concepts by defining them and giving examples for each of them. To begin, we will talk about open circuits. And an open circuit is a condition of path discontinuity. Condition of path discontinuity between 2 points. So you can think about this in terms of the circuit. It's a line where there's a space on it. So essentially, another way to think about it is if you have a person and a door, there's no current that can flow through here. The current comes, or the charge comes, and it stops. There's no current that flows through these 2 points. But I can take my voltmeter, as we learned in last class, that there's a voltage A here, or let's say voltage P and a voltage D. So there's a voltage PD between the person and the door, but there's no current that flows through that person and that door. So that's what an open circuit is. So no current can flow through an open circuit regardless of the voltage through it. And opposite of that is what we consider a short circuit. And this is a condition of complete path continuity between 2 points. So to properly define it, a condition of complete path continuity between 2 points. And there's no voltage drop that occurs between a short circuit. So in schematic, a short circuit looks like this. And if you were to measure it with our voltmeter, so V, this is point A, this is point B, VAB will be equal to 0 because the voltage at A is the same voltage at B. So that's how we defined open and short circuits. And next, within the same thinking, we have what are called switches. And these switches are similar to the switch that turns on your light bulb in your room or your fan. And there are two types of switches. There's what you call a single pole, single throw switch. And this is SPST. And essentially what happens is you can have a switch that is initially at open. So we have a switch initially at open, and then at T is equals to T0, at T is equals to T naught, you close the switch. And another example of an SPST is if you have a switch that is initially closed and at T is equals to T0, the switch opens. And another type of switch that you can have is a single pole double throw. and this is an SPDT. And essentially how that works is there's two terminals, terminals 1 and terminals 2, where at a time t equals to 0, t equals to t0, we make our switch go or move to terminal 2. So this is what you call an SPDT switch. And that's really all for switches. But this concept is very important to introduce early on in electrical engineering because it is used everywhere, from your light switch to even your keyboards. Everything is dependent on switches. So we need to be able to understand what types of switch we have and what they look like in a schematic drawing. The next topic we were going to concentrate on is power. And power, it can either be delivered or consumed. And what that means is if I have a circuit that has a switch connected to a light bulb, as shown here, where this is V battery, and this is plus charges are here and minus charges are down there. When I close this switch, there's going to be a current that flows, I, to this light bulb, where energy will be consumed by this light bulb and photons will be released at a certain frequency that we see as yellow in most light bulb cases. And this is essentially how light bulbs work. When electrons flow through the resistor or through the filament, it absorbs a current, causing it to heat up and glow, resulting in the conservation of electrical power into light and heat. So, again, just to be more formal, the first thing that happens is the battery acts as a supplier of power, and the light bulb acts as a recipient of power. And you will see that similar to current and voltages, in terms of power, the amount of power delivered is always equals to the amount of power consumed in a closed circuit. Specifically speaking, we want to go and thank a gentleman named James Watt, who lived from 1736 to 1819. He was a Scottish engineer that defined power as, so his definition for power, so def power, is the time rate of change of energy, where we say that P is equals to dW over dt, where again this D is just delta, which means change in W over change in time. And we reward James Watts by naming power in his name, or W, where, going back to some algebra here, if you have P, and let's say we do dW over 1 and multiply dW by dQ, and then we have 1 over dt and multiply this by dQ over dt, over 1, we can simply say this equation and these equations are the same, where now we have dW over dQ times dQ over dt, and the change in energy dependent on the change in source is voltage, and the change in charge over a change in time is current. So we can conclude and say P is equals to VI. So this is our general equation for power. And again, a general rule of thumb is given all elements in an entire circuit, the sum of power. So the sum of power from K equals to 1 to N P of K is always going to be 0. So if we have an example here, if we have an example that looks like this, where we have two devices, this is ground, where the voltage drop here on device 1 is 6 volts, and the voltage gain here, the voltage gain here is 6 volts, and the voltage drop here is 15 volts. And this is a battery supplying 12 volts of power, and there's a current that flows of 3 amps. We can say that the power distributed at device 1, so this is device 2, the power at device 1 is V1I1, which is essentially 18 volts times 3. My apologies, this is device 1 and this is device 2. So P1 and this is 18. So P1 is equals to V1I1 is equals to 18 volts times 3 amps, which is 54 watts. And P2 is going to equate to V2I2, which is -6 times 3 amps. I'm not going to write the units all the time, but we should know that they're there. And then P battery, so the power at the battery, or P bat, is equals to 12 times -3, which is equals to -36 watts. And again, this is negative because it's delivering power. There's a voltage gain from minus to plus. And here there's a voltage gain from minus to plus, but here there's a voltage drop from plus to minus. So the power is positive. So 54. So the sum of power is P1 plus P2 plus P3, and we get 54 plus -18 plus -36, which is equals to 0. And essentially what this means is, what we're saying is that the power received, so 54 volts received by P1 is is basically equals to the power supplied by P2 and by P3. Another example we could have is, and I'm going to write this off the video so you see a whole bunch of written stuff out just to save time. But another example we can have, so essentially this is the problem. And the problem states that a resistor is connected to a 100 volt DC power supply and consumes 20 watts of power until the switch was turned off, and after which the voltage decayed exponentially to 0. The subsequent voltage variation is this for t greater or equal to 0. And the question is asking you to find the total amount of energy consumed by the resistor after the switch was turned off, or the total amount of power as well after the switch is turned off. So the thing that I like about this problem is it uses all all the things we've learned so far. For example, the power, voltage, resistor. So it's a really good problem to solve where we consider before the switch is turned off, so before t is equals to 0, we consider that we use our power P is equals to I times V. So that means that I is equals to P over V, which is equals to 20 over 100. So that means my current is 0.2 amps. And this is, again, before the switch is turned off. And the resistor that is pulling this 0.2 amps is V is equals to V times V over I, which is equals to 100 over 0.2. So it's a 500 ohm resistor. And then after t is equals to 0, so the switch is turned off, I of t is equals to V of t over R, which is equals to 100 e to the minus 2 t over 500, which is equals to 0.2 e to the minus 2 t amps. Again, this is for t greater or equal to 0. And what we consider the instantaneous power is P of t is equals to V of t times I of t, which is equals to 100 e to the minus 2t times 0.2 e to the minus 2t. And again, this is equals to 20 e to the minus 4t watts. And as you can see, the power decays at a rate of e to the minus 4t, which is much faster than the rate for current and voltage of e to the minus 2t. And the total energy dissipated in the resistor after engaging the switch is obtained by integrating this value. So essentially the total energy, and this is kind of we're going to dive more into this, but for now, the total energy W is equals to the integration of time is equals to 0 to time is equals to infinity of P of t dt, which again, this is from calculus 1 and 2. This is 20 e to the minus 4t dt, which is equals to minus 20 over 4 e to the minus 4 from 0 to infinity. When you plug this in, we get 5 joules. This is the units. 5J, joules is the units. Explicitly speaking, this is minus 5 e to the negative infinity plus minus, actually, minus 5e to the 0. This is 1 plus plus. This is 0. So you get 0 plus 5, which is equals to 5 joules. The next topic we want to talk about is independent voltage sources, where we have a way of representing them to be ideal and a way of representing them to be real. And then we want to dive into independent current sources, where we also have a way of representing them as ideal and a way of representing them as real. So to begin, we'll start with an ideal independent voltage source. And the definition for this is a source that provides a specified voltage. across its terminals. Independent of the load or circuit connected to it. Independent of type of load or circuit connected to it. And again, this is kind of shown. So essentially, where V is equals to Vs for any I not equals to infinity. And the way we should depict this looks like this for a battery. So the charges are here, plus minus. This is Vs, or you can have it depicted like this, where it could be a capital Vs or a little Vs. And this is a DC source. How it looks graphically is something like this, where for any current I, V is equals to Vs. And again, this is I, V. And this is your ideal voltage source. But since we live in the real world, we need to consider B. So this was A. We need to consider a real voltage source. A real voltage source. And a real voltage source says that it's a combination of an equivalent ideal voltage source. So of let's just say a combination of an ideal voltage source in series with an equivalent resistance. An equivalent resistance, RS. The value for this ideal voltage source is Vs, where an example of this looks like this. This is RS, this is Vs, and essentially you have RL located right there. And this right here is what you call your real voltage source. And we have to note that RS is a lot smaller than RL. So that means that all my voltage, if RS is very small, like if RS is 1 ohm and RL is equals to 100 k ohms, all the voltage Vs is going to drop through here. But again, a realistic voltage source has an RS in series with its voltage source. Next, we will talk about ideal and realistic independent current sources, where we start with an ideal independent current source. And this is defined as it provides a specific current flowing through it. And regardless, and this is regardless of the voltage across it. And again, this is I is equals to IS for any Vs not equals to infinity. And how this looks like is an example of this is something that looks like this, IS. So this is a DC source. And we can also represent it with little is. And this is any other source, any source. And the way it looks like graphically, it's in the IV curve, is something like this, where this is IS, and it's an ideal, or IS is equals to IS, and it's an ideal current source. But again, we live in the real world, so we need to identify it in real time, what it looks like realistically. So realistic current source. And this consists of, it has an ideal current source, IS, in parallel this time with a resistor, RS. So an example how this would look like on the schematic would look like this. This is RS, IS. This is my terminals, and this is my load circuit, RL. And essentially, this is what we consider the realistic current source. And in this situation, though, RS is way bigger than RL. That's because we want that all my current should flow in this path. And in this situation, if RS is extremely big, none of the current will want to flow here. If you remember in our past examples of the highway versus the side streets, so the current is going to want to flow here because there's a lot of traffic here, so it's going to come here. So this is what a realistic current source looks like. And now we'll dive into another example where, again, I will kind of edit this out and you'll see the example on the screen. So this is what the problem looks like. We have a schematic like this, and they're asking us to use the voltage divider equation, which we will derive in chapter 2. And the voltage divider equation says VL is equals to RL over RS plus RL times VS. And it is saying that what is VL at RS is equals to 0.15 at room temperature of 20 degrees Celsius. And essentially, for A, VL is equals to 10 over 10 plus 0.15 times 1.5, which is equals to 1.477 volts. And again, this is within 1.5% of Vs, equating to 1.5 volts. But if we have a situation where we take B at T, at T is equals to negative 40 degrees Celsius. So it's, if it's really, really cold outside, and RS is equals to 0.9 ohms, then VL in this case will be 10 over 0.9 plus 10 times 1.5, which is equals to 1.376 volts. As you can see, in the case of ignoring RS altogether, would lead to an error of about 8%. So if we ignore this value, we might get error rates of around 8%, but at low temperatures, batteries are less efficient and often often cease to provide the desired voltage and currents. So again, this is why your car normally dies on cold winter days, because this resistor here becomes apparent to the circuit and draws a lot of voltage. So the voltage that's being provided to my load or to your car isn't sufficient enough, because there's the resistors, the source resistance is extremely high due to the cold temperatures. The way it looks like graphically, it will look something like this. We normally have this is as the temperature increases, so from -40, -20, 0, 20, and 40. So at 20 degrees Celsius, RS, this is in ohms, the battery resistance, let's say that this is 0.2, 0.4, 0.6, 0.8, a battery resistance of 0.15, so a little bit below 0.2 is right here. And at -40, the battery resistance is at 0.8. So that means that we get an exponential curve like this. So as the temperature decreases, the battery resistance increases. And similarly, as the temperature increases, the battery resistance decreases. The last topic we want to touch on in this lecture is what's known as dependent sources, where a dependent source, or a dependent voltage source in this case, is defined in terms of a specific voltage or current elsewhere in the circuit. So I'm going to draw out an example of a 741 op amp circuit. We haven't studied op amp circuits yet, but I just want to introduce this to show what a dependent source might look like, and also just to scratch the back of some individuals to show some examples of the things we'll get to touch on as the time goes on. So maybe get some excitement going to see that at the end of these lecture series, you'll be able to identify what something like an op amp can do. So this is the 741 op amp. This is the op amp. And this is what it looks like. And essentially, this is what you consider RS. Let's say this is 15K ohms. This is VS. And this is what you call your feedback resistor of 30K ohms. And this is your V out. When you solve for V out, when you do your schematics and your analysis of an op amp and you solve for V out, you get V out is RF over RS times VI or VS in this situation. So this would equals to -30 over 15 VS. So that means that your V out is minus 2 Vs. This is what we consider a dependent voltage source, because V out here is dependent on this Vs. If this Vs changes in any direction from 1 to 2, this V out will be amplified from 1 to 4. And actually, it would be a negative direction because it's an inverting amplifier, so this is 1 to 4. Again, it's dependent. V out is dependent on Vs. That's why we call it a dependent voltage source. Another way to look at it is a amplifier can be drawn. Again, this is just to give you a taste of the type of schematics we will be looking at. And by the end of this course, you'll be able to analyze a circuit like this and be confident with it. Another way to look at it with symbols is when we analyze an op-amp circuit, we think of the small signal analysis, and this is kind of how we draw that. Again, don't worry too much about not understanding what this circuit actually does or how to analyze the circuit. But what we want to do here is note that if we have a VI in here, this voltage here, V2, will be dependent on it. So essentially, this is what's referred to as a voltage controlled voltage source. Or VCVS, where the symbol for this is, again, just to be more clear, looks like this. And for a voltage controlled current source, the symbol looks like this. So these are the two types of symbols that you might see. And then to close out, let's do a really simple example. Imagine we have something that looks like this, plus minus, where this is 10, plus minus, that's a battery. This is my current flowing in here, I1. This is 2 ohms. This is 5 ohms. And the voltage V1 here is 4I1. The question asks us to find V1. And what we can do is we know that the current or the voltage across this resistor is in parallel with this voltage. So that means that I1 is equals to 10 volts, this is in volts, over 2 ohms, which is equals to 5 amps. And V1 is equals to 4 times I1, which is 4 times 5 amps, which is equals to 20 volts. So again, we can see that this is a current controlled voltage source, right? Because it's being controlled by a current, and it's a voltage source. It's supplying voltage, but it's being controlled by a current. So it's a current controlled voltage source. Again, a voltage, so let me draw out these symbols and we'll call it current controlled voltage source. looks like this, and its V is equals to a constant. Let's just say if C is equals to 5, just so we don't confuse C. So 5 times a current. So it's a current controlled voltage source. You can have a voltage controlled voltage source, which looks like this, and V is equals to 5 times, let's just say this is V1, V and 5 times V1. And then you can also have a current controlled current source, which looks like this. So again, the current I will be equals to 5 times I1. And lastly, we can have something called a voltage controlling current source, which looks like this, where the current source is 5 times of V1. So again, the controlling the controlling aspect is here: current control, voltage control, current control, and the source is the output. So current source, voltage sources, voltage sources. So I hope that makes sense. Again, in this lecture we talked about switches, power, independent sources, and dependent sources. I hope it was clear. If you have any questions, please post down in the comment sections below. Please like and share my videos, and please subscribe if you like the material that you're seeing and you're studying. Thank you.